Hello. This is Ayse Coskun. I'm a professor here at BU. So some of you might have been at the talk that Heidi and I gave yesterday on AI for cloud apps. So this is going to have some contextual overlap, and hopefully you'll get something more out of this even if you heard the talk yesterday. So I'm leading this project on AI for cloud apps, and this is our proposal for forward-looking problems in this space, intelligent operations in the cloud, and how to do this for better efficiency, security, and resilience. And Gianluca Stringhini, who is going to be speaking now after me, and LMB are co-PIs on this project. So, in AI for cloud apps, our vision is to bring AI into cloud operations so that we can provide from development to deployment all the way to runtime intelligent analytics to users and administrators. So is my sound going? All right, maybe this is better. All right. This is a complex problem. Cloud is layered software essentially. There's a lot of heterogeneity. There are a lot of updates. But there are also problems that repeat often, so there's some opportunity to learn from. And the data that can be collected is humongous from cloud systems. So which is good, so that there's data, but then it's challenging to collect all this data, to make sense out of it, and to make sense out of it in an efficient way to give timely feedback to users. So our goal is to accomplish this ambitious goal. And in development, the examples include giving feedback to developers as they code about what might be vulnerable or buggy or outdated in their code, as they are coding before even any deployment happens. And then at the deployment stage, our goal is to identify software that might be unintentionally installed, for instance, that might be not compliant with cloud rules in that particular cloud system, or that might be, again, vulnerable or buggy code, or just outdated code, again, that's not efficient. And at runtime, we would like to make use of runtime analytics to provide performance improvements, to provide localization of bugs, to provide results for improving efficiency, and again to detect resilience or security problems. So this is how it would look like for Jupyter Lab kind of setup. So this is not specific to Jupyter Labs, but I think it's a nice example to look at because lots of people use Jupyter Notebooks today, especially for data science type of applications. People put up their Jupyter Notebook, update something, and deploy it on a first type of class, for instance. So can we provide feedback? So the yellow line over there is showing like while you code, this is an outdated module that you should update. The orange one is showing a potentially vulnerable code because there was a vulnerable library that was installed that has some known vulnerability that should just include in your code. And the pink one is referring to potentially analyzing a performance bottleneck. Like here's the change you made, and this is why your code is slower. You can envision also expanding these type of analytics. For instance, the pink box over there not only could provide performance results, but could also provide power efficiency results if that's a metric that you're interested in. So basically, as you look at your code, you can get this feedback from coding stage, like I was saying, to deployment and then after running. So that's the vision. And how it happens is through this RTQA or real-time quality assurance framework that we've been designing. And the key part of this framework is that it's generalized as much as possible. So the entire framework doesn't have to be redesigned with every single new problem that happens, right? So problems change, security problems change, efficiency problems change, resilience problems change. So basically we want one framework where we can still use the majority of the framework, but plug in different engines. So you can put in a vulnerability scanner, a network anomaly detector, or your own analytics engine, whatever you might be interested in, plug it into this framework. And in the background for the Jupyter Lab example, for instance, there would be the client, server, and language kernels to support with the necessary AI-based engines to enable these things. So that's the overall framework. Like I said, one thing we've been developing specifically is for Jupyter Labs, but we have done much of this work also on other environments, containerized or virtualized clouds and all of that. So on the runtime analytics piece, this is a critical piece to many analytics applications to collect telemetry data or broadly data from the systems at runtime. So you can look at a graph like this, and it includes a lot of information. We actually have a visualization tool that we designed in conjunction, in collaboration with IBM at some point. So you can imagine that these are services, you can imagine that these different boxes over there are pods, or depending on the granularity that you want to look at. And then each one of these would have some logs associated with them, typically textual logs. And then you can create a trace graph using tracing tools, following request through its life cycle. And then you can get telemetry from your system, and telemetry can include thousands of different data points from different subsystems, right? So all of this needs to be coherently analyzed, we need a framework to be able to make sense out of this data and then really analyze it with cross-data analytics, and we need to feed back to the user, hey, this is what happened to telemetry, this is the anomaly we observed, and this is where it connects to in your distributed application. So that's the vision. And as part of this, like I said, one part of this project is to develop this tooling so that users and administrators can look at this data in an easier way. So one specific way of looking at this data is through distributed tracing, which has been mentioned today a few times in some other projects as well. So the purpose of tracing is to find bugs or find performance problems in distributed applications. So we can create these spans, and then eventually the goal is to localize a problem. Like, hey, this is the request that's been taking a lot of time. Now, you can do that with instrumenting everything that you can instrument, but instrumenting everything sounds scary, and it is scary because it causes a lot of overhead. Like, nobody wants to instrument everything. The other problem is that you often don't know what problem, actually, majority of the time, you don't know what problem is going to appear. So you don't know what instrumentation to place in advance. So we use learning-based methods to determine the most useful traces or trace points so that we can localize problems more efficiently by using less data. So periodically we collect trace points through applications, and there are tools for this that people use, such as Jaeger and the like. And we have done our own enhancements to enable trace points as needed. And so we collect this data. The key differentiating point in our work is that as opposed to collecting everything, all instrumentation as possible, or as opposed to enabling disabling instrumentation using a push button approach, like there's a problem, I want to collect data, we continuously want to collect data because we don't know when the problem is going to happen, but we only want to keep the relevant one. So we use the learning-based approach to build leaf distributions for each instrumentation choice. And only keep the instrumentation that's most relevant, the data that's coming from the instrumentation that's more relevant, and then you can throw away the rest without losing any information, essentially. So the insight behind this is that a vital set or the vital few is sufficient to explain most of the performance problems. So you actually don't need the entire data set. For instance, a problem like tracing. So we can focus on the few. And our results show that basically by collecting only a few percent, to like 3 to 30% of the entire instrumentation is actually sufficient to debug problems in real-world applications. So that's what we demonstrated so far. So we are continuing to building this infrastructure for more applications, for different kinds of environments, and we are working to make the overall tracing footprint even less in terms of the storage overhead business. So we talk about data. So data is a critical part to do analytics. One essential issue with data is that if I come to your company and say, give me your data, give me all your data, most likely you won't, because you don't want to release sensitive information. So this happens all the time. Let's say, for instance, network data. People might be willing to actually share some data, but maybe they are worried about releasing their location or their specific IP or some sensitive data that might be embedded with their network traces. So in this case, or network telemetry, in this case, what we offer is to generate methods that will preserve the authentic information in the data, but then it's not going to be the same private information, so we will provide differential privacy. So we want to protect differential privacy, keep the accuracy, like if I want to do a query based on telemetry to understand a network performance problem, And then I should be able to still do that, but hopefully I can do it with some privacy guarantees while shrinking the storage requirements. So one approach that we've been working on is using an autoencoder to go from the input data, and then I'm not going to get into the details, but basically, maybe this is a better overview. Get different kinds of dimensions in this data, the different types of data in this high-dimensional data set, and then design into autoencoders for each of these clusters of data, and then add noise to protect privacy and generate privacy-preserved version of this data, which the network administrator or user can then query this data for whatever type of analytics they can look at. And so we've been using some Cisco data, for instance. We were able to use 2 gigabytes of data, for instance, compressed to 60 megabytes, so several orders of magnitude reduction, and still maintain the overall accuracy in a pretty nice way for the queries for this kind of data set. So more work we are doing on this to enable privacy-preserving telemetry. Now Gianluca is going to talk about the security side.
Right. Thanks, Ayse. So yeah, as Ayse introduced very well, we have all these components that come together to provide more insights and understanding of what's going on in a cloud environment. And one of the phases of our framework, of our approach, is the deployment phase. So as services are deployed, we want to understand whether, for example, there are some vulnerable dependencies that are being deployed, or whether some dependencies might violate some compliance requirements and so on. So to do this, we developed Proxy, which is an automated machine learning-based method that essentially learns what we call file system footprints of software packages. So it learns which files are installed by which packages. It actually has some more advanced processing there. It extracts tokens, and then it uses that to train a model that can later be used to figure out if a certain known package is being installed or is installed already. And that can be used to flag packages that are known to be vulnerable or that are known to be non-compliant and so on. And Proxy is actually very accurate, and it's actually very fast, which is one of the goals that we have, because we want to develop something that can be run at scale quite easily. And so we integrated Proxy into our RTQA demo. So if you remember the architecture that I showed before, so we have several components, and basically Proxy will identify commands that will trigger this module and later provide feedback, run some analysis and provide feedback on what's going on. And so this is just an example. So we're trying to install Keras, which is an open source Python module for interfacing with artificial neural networks. And Proxy runs in the background, matches these footprints, feeds them to the machine learning model, and figures out that actually there is a vulnerable dependency. Maybe we should think twice about it or something like that. Another project that we're working on is based on the development side of things. So as people are writing code, obviously they can introduce vulnerabilities and so on. And so to stay with this AI for ops theme, we thought, why don't we try and develop AI-based techniques to detect this kind of vulnerabilities. And why do we want to do that? Well, because existing techniques to detect vulnerabilities require a lot of domain knowledge. They can be quite cumbersome, depending on what you're trying to do. You need to define sinks and sources and things like that. And the existing machine learning techniques to do this are not quite advanced. So they're specifically designed for C and C++. We want to work on Python and so on. So what we're trying to do basically is applying all the fancy AI techniques that you've been hearing about, transformers and large language models and so on, to detect vulnerabilities. And so this is just a demo of what our tool is doing right now. So as you're writing Python code, Our framework actually identifies potential statements that might be vulnerable, so in this case a SQL statement, send them to a backend, the backend runs some analysis, and if there is a vulnerability detected, it will pop up a warning. This line of code is vulnerable, you should fix. Yeah, that's the warning. Very well. Another thing that we are working on is this idea of federation. So as Ayse was talking about, companies might be reluctant to share their data. They might not be willing to tell other people, other entities about what's going on in their networks, especially if these are security relevant events and so on. So we are experimenting with federated learning to actually see if we can build a federated model that learns, by looking at all the threats that different organizations are seeing. Can we actually develop a model that can predict future attacks without actually disclosing all the security events that are going on in the organization? And so this is just a summary of the ongoing work that we have, and we have a poster outside, and so a few of us will be there to answer more questions if you're interested, or we are open to answering questions right now. Thank you.